Hello, welcome to the demonstration corner. Sorry about that, we're just a minute late. Today we're going to talk about the MPV and the measurement of thermal physical properties as well as thermal effusivity according to ISO 22007-2 as well as the new ISO 22007-7. But before we do that, as classic, we're going to turn the camera around and show you the demonstration equipment that's available in our demonstration corner and a little bit about them, and then we'll come back and talk about the MPV as well as some of the testing capabilities and the MTPS sensor, and get into a couple interesting topics. So we'll start with steady state. So this is our guarded heat flow meter for the measurement of complex materials which are typically heterogeneous and or layered materials that are not repeating through the thickness. By heterogeneous, what do I mean by that? What do I mean by that? It's not what you see under a microscope in terms of dispersion. It is more about if you were to visualize heat diffusing into a sample, is it diffusing at a constant rate or a constant rate of diffusion? If it is not, then it doesn't really, it's not really proper to term it as a homogeneous material in terms of measuring heat transfer rates. So GHFM is ideal for that. It's a guarded method, and it promotes one-dimensional heat flow across a sample that's 2-inch diameter. The thickness can vary from sub-millimeter up to 25 millimeters thick. The overall temperature range is -20 to 310 Celsius, and is a very important method for a wide range of materials. There's lots of demonstration videos on that. Conductivity range is 0.1 to 100 watts per Kelvin, so it is a very versatile instrument. Our other steady state device is for the use of insulation, measuring insulation and construction materials. It does follow ASTM C518 as well as the equivalent international standards. There's HFM 100 for measuring up to 4 inches thick or 100 millimeters thick. There's a high temperature version as well as a standard temperature version. You can add the ability to measure specific heat or extended conductivity range. And then we have another size, which is the HFM 50, which measures up to 2-inch thick or 50 millimeters. We have plenty of demonstration videos on that as well. I invite you to review those. So our MP1, which we're not going to be demonstrating today, is our advanced platform for multiple methods that are primarily designed for the absolute measurement of thermal conductivity, diffusivity, specific heat, and thermal effusivity for solids, pastes, and powders by transient plane source, the ISO, as well as liquids by the ASTM for liquids, 7896, as well as transient line source, ASTM D5334 and 5930, and transient hot strip. What is unique about this, the MPV, which has these very same methods, the MP1 has it basically across the board in terms of specifications and capability, much more advanced features in measurement terms. One of the classic features we have at the MP1 is a 4-channel switch that lets you connect up to 4 devices, which include our temperature platforms, which allow you to measure small, compact samples by those various methods I just described. So it's our advanced instrument. We call it future-proofing your thermal conductivity measurements. Our MPV, which we'll talk about when we're back. Our focused THWL1, which is for thermal conductivity, diffusivity, and specific heat, and effusivity of liquids and phase change materials. This is our focus instrument specifically for those materials with no ability to expand into solids, just focused, following ASTM 7896. This is the transient hot wire method. It does allow you to test past boiling points because you can back pressure the sensor, 20 bar or 35 bar. This has an integrated temperature platform. As it sits here, this can go from 10 to 200 C. We can expand those ranges from cryogenic up to 300 C, depending on your application. Our baby brother to the heat flow meter is our small format insulation instrument. So this is for measuring insulation. Sample size is as small as 2-inch, as large as 12-inch square. from a few millimeters to 25 millimeters thick. We designed that to be an affordable heat flow meter for narrow applications, but more importantly, when you're measuring heterogeneous, as I just described it when I was discussing the GHFM, when you're testing heterogeneous insulation, which many are, that you're using the proper method, one that's measuring resistance-based thermal conductivity. And typically we have our MP2 at the end of the bench, but that's coming back from a show. Again, our MP2 is our portable version of the MP series. Really all the same methods that our MP1 has and our MPV, just with much more narrow ranges of use. So our MPV, maybe if we come a little straight on here, we can talk about the instrument. The basic MPV, so the MPV that you acquire as a basic configuration, is transient plane source according to ISO 22007-007-2 for thermal conductivity, thermal diffusivity, specific heat, and effusivity of solids, pastes, and powders. The basic configuration also includes the transient hot wire method. So both primary methods designed for their best suited applications. Transient hot wire for liquids and phase change materials. Transient hot wire following 7896, specifically designed to measure fluids without the effects of convection. That's the enemy when you measure fluids. So we combine those two methods to create a very capable instrument. The basic configuration of it for transient plane source is up to 100 watts per meter Kelvin, and you can upgrade that to go to 500 watts per meter Kelvin. That's the MPV. So the optional methods that you can add to it are an MTPS sensor, which I'll talk a little bit more about, the transient line source for ASTM 5334 and 5930, as well as a high temperature, high pressure THW sensor for basically testing liquids under pressure or temperature. So you can test approaching or past boiling points. So today we're going to talk a little bit more about the MTPS sensor and how it relates to standard measurements, as well as the new ISO. By new, I mean 2022, so that's fairly new. The ISO 22007-7, which describes the measurement direct measurement of thermal effusivity, and I'll talk a little bit about that, for one-dimensional shape, and what the standard refers to as embedded thermal effusivity, and I'll talk about those. So what is thermal effusivity? It's somewhat of a complex discussion, but at the same time it isn't. There's just some fundamentals to understand. There is an existing ASTM standard for measuring thermal effusivity, and it's 7894, and that's for the thermal effusivity measurement of textiles and fabrics. And it has a fairly narrow range of thermal effusivity, 35 to roughly, I think, 11 or 1200 units of effusivity. What do those ranges mirror? It's fabrics up to around the thermal effusivity of about Pyrex. Pyrex is around 1,000 or 1,100 units of effusivity. So what is effusivity? The proper description of effusivity is the square root of thermal conductivity, density, and specific heat. So that's what the mathematical representation of thermal effusivity. It gets a little bit more complicated based off of the way you're measuring thermal effusivity and the shape of your sample and the nature of the sample you're measuring. So for thermal, I did a demonstration or discussion, a deeper dive on thermal effusivity by ASTM 7984, what that really is used for, and I'll repeat some of it. It's basically thermal effusivity to that committee, and the use of fabrics is to measure the sense of coolness or warmth, mirroring only a short test time, so contact of a momentary 1 to 3 seconds roughly. And it's qualitative in nature. So the very fact that you're measuring a short time scale thermal physical property, or because it has a thermal conductivity in the description, that is typically very much the requirements, the assumption of that measurement is very much aimed at homogeneous materials. But that thermal effusivity in that standard for 7984 is the closest descriptive quantity, if you will, used in a qualitative way to describe that sense of coolness. So it does fit, but at the same time it doesn't, because it can be very confusing if somebody were to take that exact same measurement approach and consider that standard and be interested in the thermal conductivity to back out of the thermal conductivity of the thermal effusivity value. So the 7984 standard, as well as the measurement of textiles and fabrics, the thermal conductivity can never be backed out of that, because by the very nature of all of those materials being heterogeneous, the thermal conductivity inside the thermal effusivity is just not accurate, even close. It can be very misleading and confusing. So, but for the use of thermal effusivity for measuring the sense of coolness, it works, at least conceptually, and it provides those designers of materials that they want to influence the sense of coolness or warmth. It provides them a way of describing the change in that sense, that surface haptic sense of coolness or warmth. So the ISO 22007-7, it expands in a much better way on thermal effusivity. And why I'm describing it as a much better way is it's taking the absolute method of transient plane source, which is the classic technique, double spiral, following ISO 22007-2. It expands on that to describe effusivity in a much more accurate way based off the application. So inside that standard, and I encourage you to look at, we'll put the link to the ISO and you can purchase the standard to read it yourself. It describes two configurations of a sample and sensor for measurement of effusivity. And we're going to talk about those. One is a one-dimensional shape. So when the diameter of your sample is equal to that of the diameter of your sensor. So in this case, we have a 12.8 millimeter diameter sensor. It might be hard to see there, but if your sample is equal to that or just slightly larger, the heat propagation is along the direction in the elongated material. We can measure the transient plane source, and the ISO describes measurement of direct effusivity. So that is referred to as one-dimensional module, and we can measure direct effusivity. And if you know the density and specific heat, or the volumetric specific heat of your sample, you can calculate the thermal conductivity. In fact, that's what the measurement is. You input volumetric specific heat from one-dimensional shape, you get a measured calculated thermal conductivity from a measured thermal effusivity, and you get the effusivity as well. So that is one-dimensional shape. So by isolating the in-plane direction and looking at a tall sample, we can measure along the length of it. That's a direct measurement of thermal effusivity. Now, why is that different from a bulk sample? Is that in a bulk sample, meaning a sample that covers the sensor at least 2 times the diameter. From a bulk sample, we can solve for thermal conductivity and thermal diffusivity directly. And then the outputs of the results are a calculated specific heat and a calculated thermal effusivity. So we'll show data from that a little bit. So from the ISO-7, one-dimensional shape for thermal effusivity. We use that quite a bit. It's very useful. It also has some strength. This is a stainless steel piece that is roughly 13 millimeters, and the sensor's 12.8, so you can see it just covers it. You measure along length. You could have different lengths of 1D rod. We have different diameters of sensors, so you could have different diameters of sample to match that. This is quite an ideal method for measuring somewhat heterogeneous materials. There are limits to what is defined as heterogeneous and what can be accurately measured. An interesting example that keeps popping up is 3D printed materials. So 3D printed metals have some entrapped air, some entrapped oxygen that would even at 99% dense, it does give you a conductivity that's different than the intrinsic solid version of the same metal. So in that case, measuring along the length of a defined dimension gives you a one-dimensional value, which is quite ideal when you're trying to characterize one material. The other version described in the ISO is short time scale. So what is referred to in the -7 standard as embedded, what that's referring to is when you have a sample that is covering the sensor and it has dimensions, so it's larger than its diameter. The key is to have short enough time scale. So I'm going to put this down and use my hands to describe something. So when you're following the ISO-7, it's very important that we satisfy this term, this unitless range called total to characteristic time. What that is, the ISO is describing that we want to measure a three-dimensional shape. So if your sensor is sitting in the center of a sample that is at least 2 times the diameter, and you're satisfying the minimum penetration, your shape of the heated diffusion, the heat inside it, if you visualize, is three-dimensional. So picture half of a soccer ball. Now, none of those edges of that heat penetrating into the sample can hit any boundaries. So from that three-dimensional shape, we can measure thermal conductivity, thermal diffusivity, and calculate volumetric specific heat and thermal effusivity. If you were to take that same measurement, nothing changed, other than reduce the test time down to a very short, so if you have a planar sensor and very short time scale, your shape is now very close to that of the planar sensor. So it's very close to one-dimensional. So that's where, with very short time scales, and that's what's described in the ISO, for very short time scales, we can measure, normalized to the sensor, 90 degrees, we can measure one-dimensional values with short time scales in a narrow range of effusivity. So again, if you try to measure one-dimensional shape on aluminum or copper, at 1 second, your thermal diffusivity is so high that it'll still be three-dimensional shape. So it's only applicable for a more narrow range of thermal effusivity. Actually, in fact, very close to that range of thermal effusivity described as 7984. It's just using an absolute sensor described in the ISO-2 instead of a calibrated MTPS sensor described in 7984. So that's the difference. So there's no contact agent needed for the effusivity measurements on short time scale or three-dimensional measurements. So in fact, this MTPS sensor that we described as the absolute version of the MTPS sensor is extremely capable. So let me talk a little bit about this. We have we will get in, there is videos of showing the construction of this, but essentially it is a double spiral sensor sitting on top of insulation, where the standard configuration of transient plane source sensor is sensor sitting between 2 pieces of the same material. So in this configuration, we have a known backing material, insulation. So we know how much heat is leaking into the backing, and that's part of the calculation. And then we measure what's on top of it as an unknown. So the MTPS sensor that is packaged as an optional sensor on the MPV, it has very unique capabilities. And all of them are asymmetric. All of them are single-sided. And some of these are proprietary. So we're able to measure. So when you buy an MTPS sensor with the MPV, it has the built-in ability to measure slabs. So asymmetric, single-sided, thin conductive sheets, one-dimensional, as we've described here, so one-dimensional thermal effusivity and thermal conductivity. That does require the input of specific heat. Bulk properties, so that would be measurement on a more typical sample that you're covering the sensor times 2 at least, as well as anisotropic, so measuring 2 directions. That's described in the ISO-2, but we can do that asymmetric. And then now with this new -7 standard, short time scale effusivity for looking at one-dimensional effusivity on lower effusivity materials. So this is Vespil. So the measurements we've set up and sort of demonstrate today are Vespil, which is in the range of 800 units of effusivity. It's a polymer. It's a well-known polymer. We're going to show the bulk measurement, because in this case, we are covering the sensor times at least 2. So we've made a bulk measurement and showing conductivity and all related properties. We've made a short time scale measurement, show it according to the -7, showing just effusivity. And of course, we hope that the effusivity from a short time scale, this is a homogeneous material, matches that of the three-dimensional calculated effusivity. They should be very close to each other. And then we've measured our one-dimensional shape for thermal effusivity. And with the input of specific heat, this is stainless steel, 304, we should get the thermal conductivity, diffusivity of course the measured property thermal effusivity. So that's a bit of a description. The point is there's a lot of interesting capabilities with this sensor and the release of the new ISO, and it's a tool set that you can use to basically measure a whole range of materials in unique ways. So we're going to spin the camera around and come a little closer. So this is the benchtop seat for the MTPS sensor, which just makes it nice and convenient. You can of course make measurements on large materials by inverting the sensor, but this is just a seat for the sensor, and it has silicone on the bottom so that it doesn't move. That's nice if you put this in an oven. I think this MTPS sensor we have here is good up to 200 C. So this one as it is, I think, is minus 75 to 200 C, so you can put this in an oven and make measurements. We're just doing it on the bench for now. So I'm just fetching the samples. So the sample setup for Vespil is not so difficult. You just center, rather for embedded thermal effusivity, or if you were doing three-dimensional according to the standard -2, you would just cover the sample, and the only thing you're changing to follow the new standard for thermal effusivity short time scales is just measuring a really short test time. Otherwise, you'd be measuring a longer test time, but staying within the dimensions of the sample. That would be your configuration, using a weight or this. We're actually going to do the setup for one-dimensional stainless steel. We're going to center it. It's going to be hard to see with the camera, but with light, you can definitely see the double spiral. And we just want to make sure we're covering that. And then I'll turn this a little bit, and I realize it might be blocking it. That's it. So I'm just double checking to make sure we don't have any exposed double spiral. And that is the basic configuration for one-dimensional shape for the MTPS sensor. Although we're going to share data on the Vespil as well. We're going to go to the desktop and show, this is our devices. So we've detected, the software auto detects the MPV. The sensor we're going to use is room temperature. We're at room temperature for now. The next screen, this is where we can put in a sample. The volumetric specific heat is 3.9. 3.9, that's the volumetric specific heat. This has a backing. The height is 20 millimeters and the area is 172. That's you need the area of your sample. Why is that important? Because if your area of your sample is greater than that of the sensor, you want the calculation to be on the area of your sample, not using the sensor. If it's identical, you wouldn't have to do that, but it's unlikely that it's going to be identical. So we're using the MTPS sensor. We're going to do a quick resistance check. Basically, this is an electrical confirmation that the sensor's in good electrical contact. The sensors are permanently set up, so unless the sensor is damaged, it would come out as good. The sensor auto detects the temperature, so right now we're on the bench. If we were in an oven, it would just record the temperature that's inside that chamber. Typically, when we're running, not doing a demo, we would run the iTPS to suggest the test time and power. But we already have these parameters for demo, so it just tends to be a time saving. Right now, we could typically run a quick transient. We won't do that. We'll just set up a schedule of 5. So we'll do 5 measurements and 500 milliwatts. 5 seconds. That is the length of time to stay within the dimensions of the sample. You could do shorter scale or longer scale as long as the penetration depth that we're calculating is less than the available, which in this case, the penetration depth is the height of the sample, which is 20 millimeters. So we can schedule that. And you'll see that our modified 1D on the MTPS sensor will measure the resistance, and that will start counting down the cool time. But the second application that comes with the MPV, which is analysis, so there's data acquisition for developing experiments and controlling the sensor and hardware. The transient analysis is where we calculate our results. So looking at the previously measured 5 measurements using the exact same parameters for that same stainless steel sample. The inputted specific heat was volumetric specific heat was 3.9, and you can see our conductivity and diffusivity. So the only real measured units here are thermal effusivity. Everything else is calculated or inputted. So, excuse me, the volumetric specific heat was inputted, and we have calculated conductivity and diffusivity. So again, this is ideal for elongated materials where you have limited radial size and samples that are larger through the thickness, if you will. It does have unique capabilities for if you have materials that are heterogeneous. It does measure an isolated amount of material, which that has its advantages. So that is the one-dimensional effusivity covered in the -7 standard. So before we move to the Vespel thermal effusivity measurement, which is the short time scale, I thought I would share that same Vespel measured at 20 seconds. So this is following the -7 standard. So the measured properties from this measurement are thermal conductivity and thermal diffusivity. The thermal effusivity and volumetric specific heat are auto-calculated from those two properties. So you can see the advantage of this measurement is you get two really important properties and the other two properties calculated. This is ideal for materials that have enough dimension to be able to cover the sensor ×2. And of course, there's a wide range of diameters to allow you to accomplish that. So this is the strongest measurement when it comes to the 3D disc. But if you want to measure short time scales, such as if you want to measure thermal effusivity of textile and fabrics like 7984, but you don't want to use a calibrated sensor, you want to use the absolute sensor, like this sensor, we can do short time scales. So this software that comes with the MPV and the MP1, it has a thermal effusivity mode, and that's for following the ISO-7. You just go into change it from common to effusivity, and then we go back to our data, and we're going to just drop these, and we're going to open up the short time scales we did on that same Vespel. So here we made 3 measurements of, we would have made more, but we just ran out of time. 3 measurements of 2 seconds at 100 milliwatts. Again, the goal is to just generate a nice clean signal. That short time scale ensures that we're not penetrating and creating a 3-dimensional shape inside the sample. It has a relatively low thermal physical properties, so you can envision that compared to the 12.8 millimeter diameter sensor, the heat of penetration is very close to 1-dimensional. So that's where that thermal effusivity result comes from. So in this case, our result is 834 as a direct measurement of thermal effusivity. We did this also with very short delays between each measurement because we were running out of time for today's. We'd probably want to add a bit more, and our repeatability would be better, but we just sort of were pushing the envelope a little bit there. So that gives you an idea of the capability on short time scales for thermal effusivity direct measurement. And again, what is the usefulness of short time scales for thermal effusivity? It's more about having the ability to measure applications like the sense of coolness or touch or warmth, and being able to use an absolute sensor to accomplish that. So I hope that it describes a little bit in terms of the new ISO and the two uses of it. Of course, the one-dimensional shape being a more widely use of that -7 standard, and certainly much more popular because elongated materials are very common. And so to be able to measure an isolated one-dimensional shape has several advantages. Isolation, heterogeneity, even directional properties. So if you take an anisotropic sample and take out cores in each direction, you can say that you're measuring an isolated direction for that anisotropic sample. So it has advantages, for sure. That's the end of our discussion today. What we'll do, just to demonstrate the true repeatable capability of this, we'll run a series of measurements with a little bit longer delay time between each measurement. What does that delay time mean? It means the heat we introduce from each measurement, we don't want that heat from one measurement to interfere with the next measurement. We want conditions to be isothermal. So we'll repeat this and put some data up on the description underneath to show sort of what repeatability you can expect on short time scales. Otherwise, thank you for your time, and if you have any questions, please get a hold of us.